Hi viewers at home, you are welcome to the GMAT41's YouTube channel. In our previous basic physical chemistry class, I taught you the Boyle's law, one of the ideal gas laws, where we studied the relationship between the pressure of an ideal gas and its volume under a condition of constant temperature. In this video lesson, I'll be teaching you Charles' law, a law propounded by Jacques Charles in an attempt to study the relationship between the volume of an ideal gas and its temperature under a condition of constant pressure. And so I would like us to state Charles' law and then move on to establish the mathematical equation that is needed in order to solve problems related to Charles' law. Charles' law states that the volume of an ideal gas is directly proportional to its temperature, provided that the pressure of the gas is kept constant and the mass of the gas is fixed, that is also constant. So you see from this law, Charles is telling us that the volume of an ideal gas will be directly proportional to its temperature if we keep the pressure of the gas constant and the mass of the gas constant. So to achieve Charles' law, it is necessary or it is required that in the experiment, the amount of the gas we use, which in this case is quoted as mass and can also be converted to moles, alright? And the pressure of the gas are expected to be constant. When this is the case, the volume of the ideal gas will have a direct relationship with its temperature. And what does that mean, that volume is directly proportional to the temperature of the gas? It simply means as the volume is increasing, the temperature will also be increasing. Okay, what if the temperature decreases? Again, the volume will follow the same pattern. The volume will decrease. Having stated this law, we want to find out the mathematical equation that guides this law. Remember, our interest is to study the relationship between the volume of the gas and the temperature of the gas. So let us look at this. Volume is directly proportional to what? Temperature. Mathematically, using the knowledge of direct variation of mathematics, we are going to have that V is proportional to temperature. This is direct proportion. Remember, under Boyle's law, for inverse proportion, it will be 1 over the other quantity. So for direct proportion, it will simply be a straight relationship, nothing like 1 over. So V is our volume of the ideal gas and T is the temperature of the ideal gas. So we are going to remove this proportionality sign, this variation sign, and to do that we will introduce a constant. I shall use K for that, and then also introduce equality sign. So this is going to give us V equal to K times T, which is KT. So I want to take note of this. This is an equation for Charles' law. Okay, what if I make this constant of proportionality K subject of the formula? If I do that, of course, to make K stand alone, I'll divide this side of the equation by its coefficient T and divide it by T also. So this is going to give us V all over T equal to, dividing here by T, K will be left. So take note of this. Let's have this as 1A and then let's take this as 1B. Did you remember under Boyle's law, I stated that whenever a quantity is equal to a given constant, mathematically it allows you to write that quantity in different states. And we decided to choose the state as initial state and final state. So we shall use subscript 1 and 2 to represent the initial and the what? Final states. Now, looking at this, V over T is equal to K, a constant of proportionality. And so we are going to write this V over T, this quantity, in its initial and final state. For that, we are going to have V1 divided by T1. Since V over T is equal to constant, it means that this is also going to be V over T, unchanged. Are you following, right? It is only the state that will differ. So this is going to be V2 all over T2. And of course, we can continue this as V3 over T3. It can go down to continuously to Vn over Tn, depending on the number of states that the gas can exist. If we say, okay, the volume of the gas when the temperature is 10 degrees Celsius, the volume is, say, 50 centimeter cube. Now, if the temperature, let's say, decreases to, say, 5 degrees Celsius, the volume is also expected to decrease from that 50 cm cube to any value. Okay, let me assume 35 centimeter cube. Okay, we can move on to say in another state, let the temperature decrease again, for example, to, let us assume 2 degrees Celsius. Again, the volume in that state 3 will also decrease from 35 centimeter cube. Okay, let us assume to 20 centimeter cube. I'm just assuming anyway. Okay, what if in another state, we now say that this particular gas, the temperature has now increased, okay? Let us say to 70 degrees Celsius. Then we expect the volume of the gas to increase from that 20 centimeter cube, all right? Which is state 3. Now the gas is in state 4, where the temperature is 70 degrees Celsius. We expect the volume to increase, okay, to even more than 50 cm cube it was in state 1. So this is what we are trying to look at according to Charles' law. However, for calculation purposes, we would simply be interested in this initial state as subscript 1 and then this as subscript 2. Then we'll take it as initial and final, at least for this stage of learning. When we move into thermodynamics in this course, you would see that it's possible for a gas to exist in more than 2 states. And that is why I gave you this general expression. So we can just say, okay, picking just these two, V1 over T1, which is the initial state of the gas, will now be equal to V2 all over T2, which is the final state. We're going to call this equation 2. Permit me to asterisk it because this equation is very important for calculation purposes at this level. And so this is the equation used to solve a problem under Charles' law. And this explains this law we have here, the Charles law. Now look at the various expressions we have. V is directly proportional to T. So this is an expression for Charles' law. Then V equal to KT. This is an equation for Charles' law. V over T equal to K, also an equation for Charles' law. And then this also a general equation for Charles' law. And then coming to this, when we decide to just consider states 1 and 2, taking them as initial and final states, we have this equation for calculation purpose, also the equation for Charles' law. So you want to take note of that. Is that okay? All right, at this point, I would like us to quickly take a look at the graphical representation of Charles' law, which tells us that volume is directly proportional to what? Temperature, if pressure is kept constant. Please take a look at the screen. Now you can see this graph. Now we've plotted volume against temperature, okay? And you can see how the graph goes, a straight line graph, a positive graph. But this time around, the graph has an intercept. And then I just decided to show the intercept on x-axis. And at that intercept of x-axis, where the straight line graph cuts the x-axis, remember the x-axis represents temperature, so you can see that's temperature. And so the straight line cuts the temperature axis. You can say that that value of the intercept on the temperature axis is minus 273 degrees Celsius. Minus 273 degrees Celsius. Now, minus 273 degrees Celsius, if you add 273 to it, what would you get? 0 Kelvin. Generally to convert from degrees Celsius to Kelvin, you add 273 Kelvin approximately to a degree Celsius value, and then you would get the value of that temperature in Kelvin. So at that intercept of minus 273 degrees Celsius, if we add 273 Kelvin to it, that changes to 0 Kelvin. Okay, and that of course is the value at that point. You want to take note of that, the intercept on the temperature axis. Alright, we are going to take a question on Charles' law and then see how we apply this equation 2 asterisk to solve problems.